The metrics for regressors that we're going to talk about today include linear correlation, also called Pearson's correlation, mean absolute deviation and its close cousin root mean squared error, and information criteria, including the Bayesian information criteria and AIC. Linear correlation is, when A's values change, does B's values change in the same direction? And it assumes a linear relationship. So it assumes that it's not going like this. So what's a good correlation? 1 is perfect. 0 is no correlation at all. There's just no relationship. -1 is perfectly negatively correlated. In between, what's a good correlation? Depends on the field. In physics, a correlation of 0.8 is something you have to be depressed about. In education, a correlation of 0.3 is something you can be excited about. Why are small correlations okay in education? Is it just that we're inferior to physicists? I'll ask my dad, he's a physicist. Lots and lots of factors contribute to just about any dependent measure. So let's look at some examples of correlation values. As you can see, 1 is just a straight line. It can be any slope except for flat. Couldn't be this either. But as long as it's going up, it's 1. If it's down, it's -1. You can see 0.8 has more spread, 0.4 has a little more spread still, but you can kind of still see a pattern, and 0 is just a blob, and then 0.4 going the other way, -0.4 and -0.8. So as you get more close to 1 or -1, you get more focused. And you can see that all the lovely stuff at the bottom all has a correlation of 0. You can also say that correlation is relatively vulnerable to outliers. So all of these 4 have the same correlation. These are taken from John Barron's. You can see the first one in the top left kind of looks like a nice spread out on a clear line. The one right below it looks like that same line, but you notice the best fit line doesn't actually fit the line. It kind of gets dragged up by that one outlier. That curve that kind of curves back down has the same correlation, and that one that has vertical points and 1 point at the end. So John would say, if he was here today, that you really want to look at a scatter plot, and except for the fact that I would say that for really big data you might want to look at a heat map, I totally agree with John. R-squared is another measure you might see, and R-squared is just the correlation squared. It's also a measure of what percentage of the variance in the dependent measure, the predicted variable, is explained by your model. If you're predicting A with B, C, D, and E, R-squared is often used as the measure of model goodness rather than R. Really, it's just R-squared. There are special cases where that's not true, but they're not relevant here. Anyways, which one you see, R-squared or R, depends on the community. Another pair of key metrics are RMSE, the root mean squared error, and MAE, the mean absolute error, sometimes also called the mean absolute deviation. The mean absolute error is simply the average of the absolute value of the actual value minus the predicted value. So in other words, for every data point, you take what the actual value was, and you find the difference between that and the predicted value. And it doesn't matter whether it's bigger or smaller, because you're taking the absolute value. Once you have the differences between each data point, actual value and its predicted value, then you take the average of those. The root mean squared error is very similar. What that is you take the difference between the actual value and the predicted value, and you square it. You average that, and you take the square root. So the difference between the mean absolute error and the root mean squared error is they're both taking the differences between each data point's actual value and predicted value, but in the case of the mean absolute error, you're just averaging those. In the case of the root mean squared error, you're squaring those, averaging them, and then taking the square root. So let's talk about the differences between mean absolute error and the root mean squared error. The mean absolute error tells you the average amount to which the predictions deviate from the actual values, which is very interpretable. Root mean squared error can be interpreted the same way, mostly, but it penalizes large deviations more than small deviations. However, there are good reasons to prefer root mean squared error, even though it's a little harder to interpret on the face of it. The example to follow, which discusses that, is courtesy of Radek-Pelinek at Masaryk University. Take a student who makes a correct response 70% of the time, and 2 models, Model A, which predicts 70% correctness, and Model B, which predicts 100% correctness. That is to say, the student's always going to get it right. So in other words, 70% of the time the student gets it right, their response is 1, and 30% of the time the student gets it wrong, their response is 0. And again, Model A's prediction is 0.7, the same as the proportion the student actually gets it right, and Model B's prediction is 1. Now, which of these seems more reasonable? Most people would say it's model A, because model A makes the exact same proportion prediction as the actual data. So let's look at the mean absolute error for this example. 70% of the time the student gets it right, so the response is 1. And model A predicts 0.7, so the difference between 1 and 0.7 is 0.3, so the absolute error is 0.3. Model B predicts 1. The difference between 1 and 1 is 0, so the absolute error is 0. The other 30% of the time, the student gets it wrong, so the response is 0. Now model A predicts 0.7. Difference between 0.7 and 0, 0.7. So the absolute error is 0.7. Model B predicts 1. So the absolute error is 1, 1 compared to 0. So when we look at how well the two models do, model A is 70% wrong 30% of the time, 0.21, and 30% wrong 70% of the time, 0.21, for an overall mean absolute error of 0.42. Model B is completely right 70% of the time and completely wrong 30% of the time. So that's 0 plus 0.3 for a mean absolute error of 0.3. So according to mean absolute error, model B that says the student will always get it right is better than a model that actually says a student who gets it right 70% of the time should get it right 70% of the time. That just doesn't seem right. Let's compare to RMSE. With RMSE, the student gets it right 70% of the time. Again, the response is 1. The squared error for that is 0.09, 0.3 squared. Model B predicts 1, the squared error is 0. The other 30% of the time, the student gets it wrong. Their response is 0. So model A says 0.7, the squared error is 0.49. Model B says 1, the squared error is 1. 1 times 1. So let's look at what the root mean squared error is here. Model A says that 70% of the time there's a mean squared error of 0.09, and 30% of the time there's a mean squared error of 0.49. So we can add those together and get a mean squared error of 0.21, which we could then take the square root of. Model B says that 70% of the time there's an error of 0, and 30% of the time there's an error of 1, which leads to a mean squared error of 0.3. So according to RMSE, model A is better, and that should kind of match our intuitions, because model A is predicting that the student will be right 70% of the time, and the student is, whereas model B is predicting the student will always be right, even though they're only right 70% of the time. So this does seem more reasonable. RMSE is coming up with a more reasonable result than mean absolute error. Now, you should note, having thought about this, that a low root mean squared error is good, whereas a high correlation is good. What does it mean? Well, a low root mean squared error or mean absolute deviation and a high correlation means you got a good model, and you can kind of go thumbs up and you're happy. A high root mean squared error or mean absolute deviation and a low correlation means you got a bad model. What if you have high root mean squared error and high correlation? In that case, your model goes in the right direction, but it's systematically biased. For example, let's take a model that says that adults are taller than children, but that adults are 8 feet tall and children are 6 feet tall. This model correlates well, but the root mean squared error or mean absolute deviation is a bit off. What if you have a low root mean squared error or mean absolute deviation and a low correlation? In that case, the model values are just in the right range, but the model doesn't capture relative change. This is particularly common if you don't have much variance in your data. So, which one should you care more about? A lot of people like root mean squared error better. I happen to think correlation is more important as long as your data is the right kind of data for correlation. Now let's talk about information criteria. BIC, the Bayesian information criterion, makes a trade-off between the goodness of fit and the flexibility of fit, or in other words, the number of parameters. The formula for linear regression, called BIC prime, is a function of your number of students, or number of data points, and your number of variables, and also of your correlation. So BIC prime has some nice interpretability. If you've got a value over 0, then your model is worse than expected given the number of variables. If you've got a value under 0, then your model is better than expected given the number of variables. And you can use them to understand how significant a difference is between two models. It turns out that with BIC prime, if you have a difference of 6 or 10 between your models, that's equivalent to having a statistically significant difference, according to Raftery. AIC is an alternative to BIC. AIC stands for, first, an information criterion, Akake 1971, and later, and somewhat modestly, Akake's information criterion, Akake 1974. It's nice when you're the one who invents the method. You can name it after yourself. Akake's information criterion makes a slightly different trade-off between the goodness of fit and the flexibility of fit. So AIC or BIC, which one should you use? Yeah. Powers says that the idea of looking for a single best measure to choose between classifiers is wrong-headed. And I would say the same is true about regressors. Regardless of what kind of model you're building, try to understand your model across multiple dimensions, and that involves using multiple metrics.